Hello everyone. So today what we are going to see is what is the density of a liquid. In simple terms, we all know that the density of a substance here, liquid, is its mass per unit volume. The mass distribution will not be uniform in the case of a fluid because the structure of a fluid is not well defined as compared to solids. Therefore, the conventional definition of density as written here goes like limit delta V tends to 0 delta M by delta V, where rho, M and V have their usual notations. Now if we say that we take a particle which is very small, as it is shown here that delta V is 0. My question is, will it replicate the whole volume or the whole fluid, or shall we take a volume which is very large which incorporates everything? So let's check it out. So if we are going to calculate density of a fluid, now we have two cases. First is we take a sufficiently small volume, or second case is we take a larger volume. Now let's see what happens in these two cases. Now suppose we want to calculate our density in this case 1. Let's say that this is our case 1 and this is our case 2. Now in this one, if we want to calculate our density, so suppose we have chosen this volume to calculate the density of our fluid. Now in this volume, what's the problem is that here we can see that this is having some mass, let's say M1. But in a same volume at a different place, the mass is M2. Therefore, what is happening is, if we take the representative volume of the same size at two different locations, we are having a considerable difference in the masses that is there in this volume. Therefore, what will happen is, if we calculate the densities, it will give us the value of a density different at different points, which should not happen. Consider the case 2. Now here we have a sufficiently large volume. Now if we calculate the density of fluid, we will see that the mass distribution in this volume as well as this volume, where both the volumes are same, is approximately equal. Therefore, if we take a volume anywhere in this place, this will give us more or less a same value of the density. Therefore, it is more correct to choose a density in where the size of the volume is somewhere bigger than this smaller one. Now what happens if we further go to a larger value? Will it be more accurate? Let's check it out. So here we have a graph. In this graph, the x-axis represents the length scale and this y-axis represents the density. Now if we take the particle size to be very small, we can see that the variation in this density is quite high. But after a point of time, this deviation tends to cease. Therefore, after this point, if we take our particle size, then the density is approximately looking constant. Therefore, we have already discarded the definition of the density of a fluid as rho equals to delta V tends to 0 limit delta M by delta V. Therefore, what should be the new definition? It is like, if we take delta V tends to 0, then our density will fall in maybe this region, which will give us a very deviating picture of density as we take the densities at different points. Therefore, we don't take the volume, our limiting volume in this region, rather we take our limiting volume in this region. So therefore, the new definition of our density will be rho is equals to limit delta V tends to the representative elementary volume. Here representative elementary volume is the point from where the deviation ceases, delta M by delta V. Now let's say that this point corresponds to a length of L star. Now corresponding to this L star, if we take the volumetric terms, it will be V star. Therefore, V star is our representative elementary volume, for which if we calculate the density will be constant for a longer length scale. I hope this cleared your doubt about density of a fluid. For more such content, please like, share and subscribe. If you have any doubts, tell us in the comment section. Thanks for watching. Have a nice day.